Okay guys, the last MATLAB programming practice would be central limit theorem. Okay, so then let's quickly review the CLT first. Okay. Suppose there are capital T IID random variables, okay, and they are denoted by x1, x2 through x capital T, okay, and their mean is mu and the variance is sigma square. Okay, so then their mean and variances are given, but but we have no idea from what kind of distribution these random variables are drawn. Okay, okay, and then for example, suppose there are two random variables, okay, x1, x2, and then their sample mean is given by s capital T. I'm sorry, x bar, simply x bar. Okay, so there, and its mean is simply is mu, right? 1/2 times expectation of x1, 1/2 times expectation of x2, and expectation of x1 and x2 are both mu. So then 1.5 mu plus 1.5 mu. It must be mu, right? And variance. In computing variance, then 1/4 times sigma square plus 1/4 times sigma square. So then variance of x bar should be 1/2 times sigma square, right? So then the mean of the x bar is mu, the variance of x bar is 1/2 times sigma square. But still, we have no idea what kind of distribution is, right? So then also this distribution usually is different from this one, right? Okay. And then what if the capital T3? So then sample mean of the three random variables, right? So then the expectation is still mu, right? And variance is now 1/3 times sigma square, right? Still, the we have no idea what kind of distribution is, right? The distribution is unknown, right? And sometimes even if this distribution is known, but this one is not standard, which is not found in any statistics textbooks, right? However, according to the central limit theorem, then the distribution of x bar is normal. Okay, like this. The sample mean is 1 of capital T times the sum of the random variables, right? And the expectation is still mu, as always, and variance is now 1 of capital T times sigma square, right? So right here, so if the capital T is 3, then the variance is 1 of 3 times sigma square, and if S bar is the sample mean of two random variables, then the variance is 1 over 2 times sigma square. Likewise, here, the variance of X bar is 1 of capital T times sigma square, right? So then still, right? So we have no idea what kind of this distribution is. This distribution of X bar is unknown, although its mean and variance are known, right? Okay. And then let's do the standard deviation here. So mean of S bar is mu. So then S bar minus mu has mean of 0, right? And then let's divide standard deviation on both, right? So then 1 of capital T over sigma squared times x bar minus mu must have the mean of 0 and variance of 1, right? Variance of 1, right? Because this is the standard deviation sigma over square root of capital T. Okay, and according to the CLT, then this random variable converges to what? Converges to standard normal, so, right? Whatever the underlying distribution is, this one, whatever this is, whatever the distribution of the xi's, it's a sample mean or a normalized sample mean, a sample normalized sample average follows standard normal distribution. Okay. By using MATLAB programming, we are going to test or just examine the CLT. Okay, just to verify this theorem. Okay, using just one particular example, right? So here is the algorithm. Okay, to test this CLT. Okay, we are going to specify sample size, and then again here we would like to see how this random variable is distributed. So then to see its distribution, to see its distribution, we need to draw, or we need to plot the histogram. To plot the histogram, what do we need? We need samples. We need samples from or drawn from or generated from this distribution, right? Okay, so here we need to specify the simulation size. So how many samples do we need? Just we are going to pick n as like 10,000, 100,000, whatever. Okay, the more the better. Okay, so we are going to specify sample size. This is sample size. I mean the samples are, I mean how many xi's here, capital T, how many random variables. Okay, right, and then this is the samples from these random variables. Okay, and then we know true mean and true sigma square. Okay, again, so the mu and sigma square are given, right? There's no uncertainty about mu and sigma square, but what we don't know is the name of the distribution, right? Even if the mean and sigma squares are the same, but the distributions could be different, right? Right. So then, given capital T and mu and sigma square, we are going to draw capital T random samples. Okay, and then compute sample mean of sample average. I'm sorry, sample average. Okay, given sample average, we can compute this normalized sample average. Can we do this? Do we have X bar? Yes, we have X bar. And do we know mu? Yes, we know mu. And do we know the capital T? Yes, yes. And do we know sigma? Yes. Then we can compute this one, right? So here, at this step, we have 7 random variables. I'm so sorry. We have capital T random variables, right? And we compute its sample average. So this is 7. So this is capital T, and this is what? This is scalar. So is this one. This one is also a scalar, just 1 by 1, right? Then we go back to step 1. Then we draw another capital T random variables independently from the previous independent of the previous iteration. So we have another independent capital T random samples, and we compute sample average and its normalization and save it. And we repeat this how many times? N times. Okay, 10,000 or 10,000 or the 100,000, whatever. Then using these n samples of what? N samples of this normalized sample average, we are going to plot the histogram to see whether the histogram looks like standard normal or not. Or of course you can compute sample mean and sample variance to see whether its mean and variances are 0 and 1, right? Okay, right. Okay, then Right, so then the yes,